All right, it is 12 o'clock. Good afternoon and welcome everyone to Ag Forestry to Go for our webinar today on soil health. We are so excited that you're here with us. I want to just touch base on a small logistical issue. So throughout the presentation, we ask that you use the Q&A function instead of the chat function if you have any questions. If you have questions throughout the presentation, we'll be monitoring them. If they're appropriate to interrupt our speaker, we'll go ahead and do that. If not, we'll save questions to the end. And if we do have too many questions to get through, we will collect those questions, get them answered, and we'll send them out with the recording later this week. So without further ado, I would like to introduce you to our speaker today, Nathan Stacey. He's a postdoctoral research associate with Washington State University at the Center for Sustaining Ag and Natural Resources. He earned his PhD in soil science from WSU, and he conducts field research where he evaluates various recycled organic materials as soil amendments. He frequently creates and participates in educational programming for farmers, gardeners, and professionals. And he has a particular interest in understanding and improving urban and ag soil health. So thank you so much for being with us here today, Nathan.
Oh, it's a pleasure. And let me just double check. You can hear me. Great. And you can see the PowerPoint. Excellent. Okay, good. Technology, one never knows. So I am Nathan Stacey, as Hannah mentioned. I'm a postdoctoral research associate at CSANR. And I'm generally located at the Research and Extension Center in Puyallup, though we have research projects all over the state. So both east and west, north and less so in the south, but pretty much all over the state. I will give you, well, I guess I've been with WSU for like almost 10 years now, and I will kind of dive into a little bit of my background briefly, not to bore you all, to explain how I've kind of gotten to where I'm at. So I am originally from St. Louis, Missouri, born and raised, left there at about 18 and haven't been back. Great place to visit, but moved all over and have lived all over the country really over the last 30 something years, 20 something years. I actually got my undergraduate degree in journalism. I wrote for a very small newspaper after I moved from college to a small town in the mountains where the most important story or the headlines were when the moose walked across the highway. It was like a 900-person town. So I wasn't the best journalist, I guess. At that same time, I had moved to Colorado and kind of was a ski bum for about 3 years working at the ski resort there in Winter Park, Colorado. And during the summers, because that was a seasonal job, I started working at one of the local golf courses in that valley. And that is actually where I kind of spawned my interest, not only in science, but particularly in soil science. So I did that through the off season in Colorado for a number of years. And I really liked that work. It was interesting. There was math involved, but there were some physical parts of it. It was kind of a fun job to do. So I went to a trade school in New Jersey, which focuses on golf course management. I got there and realized that I really liked the soil part of science and ended up moving from New Jersey to California, did some work in California on a golf course, then got out of golf courses and kind of did some landscaping work, decided that I want to go back to school, ended up in Washington, where I did my PhD work with biosolids and really focused on soil science there. And, oops, the wrong direction. And after getting my degree there, I decided that it was time to do something that I thought was helpful for the world. So I got into agriculture and have been doing that for, I think it's 4 years, but I've had background in soil for probably 6 or 7, but specific research and different systems within agricultural. And as Hannah said, with kind of different approaches, which I'll get into here in a bit, but that's where I'm coming from. And I've been focused on that for a while. So one of the things that I'm going to admit as my bias is that I come to this, not only agriculture, but in even horticultural perspective, or from the golf course perspective, I'm more interested in what's going on underground, then really on top. Agriculture is important to have a good crop yield, but I'm focused on what's going on above ground, viewing it through the perspective, what we like to call as an edaphic perspective. So anything that I'm going to talk about today, I'm going to be biased towards the soil. I think it's important. It's been shown that it's important, but I'm also specifically interested in those processes. And so again, I'm admitting my bias clearly here. I'm going to be talking through the soil perspective, and I'll try to point out those biases as I go through and where you could view things a little bit different if you were coming from a different perspective. But again, edaphic, that's the fancy word, and that's where my bias is. I'm coming to this through soil science. So why don't we just talk about what soil does for us very briefly. Of course, if I have an interest in soil scientists, I'm going to pump up the importance of soil. So what does soil do for us? Well, it does a number of things. It provides nutrient storage and transformation. It's also responsible for water filtration and storage. Simple things like physical support for plants. Really interesting and dynamic things like habitat for different soil microorganisms. And again, simple things like structural support for buildings and roads. So we're using the soil in a lot of different ways. On a global or planetary scale, it's also an interface for gas exchange between the atmosphere and geosphere and contributes to planetary nutrient cycling. So on a small scale, we build stuff on it, we grow stuff in it, but it's also interacting with the larger cycles in the planet. Really critical component of our ecosystems. So with that, and again, from my perspective, what's critical to think about when we're thinking about soil is to understand that it is a resource and that we as farmers or land managers or even researchers can either exploit the soil and degrade it, or we can take care of it and foster it so that we continue to get those functions that I mentioned from the soil itself. Again, my bias, love the soil. So why don't we talk about farming in general, because that's what we're going to talk about in this webinar, and then we'll get to soil health. But what does farming do from a very high level general perspective? If I have a forest, as you see on the slide on your left, or maybe that's your right, and I cut down that forest and then I start using that forest for agriculture, we know that that is a big land use change. It is responsible for, if you do nothing, let me be clear, if you do nothing to the soil and you just chop everything down and you start tilling and growing whatever the crop may be, and you do nothing to the soil to help it, you're going to have problems with erosion and loss of soil organic matter. This has been studied and agreed upon for a long time. That's just part of the process. So that's where we start, is we know that there are things that are going to occur because we're already doing something different in that system that we have to be aware of. Now, as a farmer, and again, I'm not a farmer, and a farmer might have something else to tell you what they worry about, but sometimes if we think about these topics and split them up, it's a little bit easier. So when I think about farming, there are a couple of things that I think about that we need to approach the soil. So we need the soil to be fertile. And there's a lot of topics underneath of that large topic of soil fertility, how we manage it, how we get that soil fertility. Oftentimes we have to deal with pest control in our crops. And lastly, we can think about weed pressure, because that can inhibit successful crop production. So the second topic there, pest control, I personally do not do a lot with pest control, so I won't talk too much about that. And I'll talk a little bit about soil fertility and weed pressure with some of the projects that we've worked on. But again, pest control is not really in my purview. I don't really deal a lot with pest control. So when I started to think about how to present some of this information, I know Brad Bailey, who was going to be here, was going to talk a little bit about organic farming. So I just wanted to mention kind of approaches to managing the soil. So as I said, we're going to come at this through an edaphic approach, and I'm going to provide you with some information on management and then how we evaluate that management in soil health and how that all ties together. But what I like to think about this approach is like an ecological soil management approach. So there can be different management strategies and different perspectives that are utilized in farming and agriculture, and there are different ways to define them. We're going to come at this through like an ecological soil management, but let's review some of the topics that are out there. As I thought about this, I decided, well, let me go over some of the more popular terms and things that are utilized today in agriculture. So organic farming is one of those topics, and I'm going to break this down pretty simply, pulling this from the USDA's website and definition. Important to note, I am not a policy or a regulation person. So if you have specific questions about organic regulations and guidelines, I can direct you to the right person later, but that's not what I deal with. Back to the organic farming. So organic is a labeling term, simply, for approved methods that integrate cultural, biological, and mechanical practices. And those cultural, biological, and mechanical practices foster the cycling of resources, promote ecological balance, and conserve biodiversity. Synthetic fertilizers, sewage, sludge, irradiation, and genetic engineering are not used. So those are prohibited when something is labeled as organic. It's important to note too, and we've worked with some farmers like this, that even if you do not have the organic certification, let's say you're a traditional farmer, you can utilize management practices that are defined as organic, and you may not meet the criteria or you don't want to apply for the organic certification, but that doesn't mean that you're not thinking about these types of approaches and you can't use these types of approaches. On that note, you may have heard, actually, let me get into the strategies first. So how do we address those? How do we get to those goals, and what strategies do we use in organic farming specifically? So when we're talking about soil fertility, that main level I talked about, we think about crop rotation, intercropping, cover cropping, mulching, and utilizing soil amendments. And I have a guess that many of you have heard of, or at least had some familiarity with all of these topics. And I'll kind of touch on a little bit some of them later, and some of the research that we've done in each one of these topics. So with the pest control, as far as organic farming is concerned, there are biological controls and natural pesticides. And then to deal with weeds in organic farming, they optimize strategies to use mechanical cultivation, seed timing, when do you get that seed out into the field that can beat the weeds, transplanting into the field instead of putting the seed out, or flaming. So those are just some of the strategies and approaches that are utilized in organic farming. But then, as I said, I thought it best to present two other approaches, and these are more concepts than the organic farming, which has a set of regulations and guidelines. So what you may have heard about as well is conservation agriculture. Now, conservation agriculture has really three principles, and those are to minimize soil disturbance, to have continuous soil cover, which may be cover crops or may just be some type of mulch or an amendment over the soil, but we want to keep that soil covered, and crop rotation. So after looking at organic farming and then conservation agriculture, you'll see there are kind of concepts and strategies that are similar across those. In addition to conservation agriculture, and I would say that this is probably has gained a lot of steam maybe in the last 5 years, and it's fairly popular depending on who you talk to. There's the concept of regenerative agriculture. So regenerative agriculture includes tenets of that conservative agriculture. So just let's go back, minimize soil disturbance, continuous soil cover, crop rotation. So those concepts are part of regenerative agriculture. They incorporate livestock into this system. So it's a managed grazing so that something is not overgrazed. They also incorporate trees, for a simple way to describe it. So agroforestry is a perspective in regenerative agriculture. And they also have, along with organic farming, minimal inputs. Again, there are strategies and concepts that are continuous through these ideas, including intercropping, cover cropping, soil amendments, keeping the soil covered, trying to minimize disturbance on the soil. Organic farming, though, has its own set of guidelines that you must meet to be certified as an organic farmer. I'm sure that many of you are familiar with this. Those are guidelines that are created by a board that looks at all these processes. So again, regenerative agriculture and conservation agriculture, mainly ideas and concepts, but organic farming is actually a system that you can apply for or apply to your farm and utilize those strategies. And actually you have to apply for the organic certification. So in our work, as I said before, we kind of take the approach of ecological soil management. How can we use different strategies from those I've mentioned here and improve the quality or the health of the soil? I will also define soil health later in the presentation, but soil quality and soil health are about the same thing. There's some arguments in the literature about what those definitions are, but for our discussion today, I will probably interchange the two, but just because I talk about it so much, but soil quality and soil health for this discussion are going to be equal. So what do we do in some of the research that I've conducted? As I said, we work in the east side and the west side of Washington, and we've worked with organic farmers. We've worked with conventional farmers who are taking or utilizing those organic approaches, but it may not necessarily be certified. We've worked with very small farms that, they're diverse, small farms, large onion production on the east side of the state. Recently, we have participated in studies with integrating livestock, and that's in particular on the east side of the state and onion production. And in some of these topics that I'm just going to touch on briefly, I'll show some data and I'll describe briefly what the experiment is. I don't want to carry on too long about the stuff that I'm working on just because it interests me. It may not interest you, but I'd like to make sure I get to the latter part of the presentation and we discuss what soil health is and what those metrics are for measuring soil health. We have a project that includes a livestock integration. And so in this case, in this project, we planted a cover crop and then allowed goats to come in and mow that down instead of using a flail mower. And then we grew a cash crop after it. This was kind of a short-term study over 1 year, and there's only really 2 reps, but I'll just show one bit of information. We looked at both the cover crop biomass and the cash crop. So what you're seeing here is the cash crop biomass, and on the right-hand side, that's N in pounds per acre that were supplied to the system. So left-hand side of your screen, dry weight pounds per acre. On the y-axis, x-axis is graze and mow. We didn't see really any statistical differences in the dry weight of the peas and oats following that trit and Austrian pea, which is the cover crop, and that grazing. No statistical differences in between the graze and mow portions in the N in pounds per acre. Again, this was a short-term experiment, 1 year, 2 reps. And really what this is practice for us to apply for a much larger research project. We hadn't done really any livestock integration yet. What we found out is that the goats don't like small paddocks. We had tried to replicate it, and they like much larger areas. So in many ways, some of the research that we do is for us to learn how to do a bigger and better project, and that's certainly true here. We'll be taking this information and trying to do a much larger project where we have livestock integration on large, like quarter-acre circles. But again, we had to kind of figure that out. Not much information as far as extension or trying to provide some data, very little, but much better information for us as we try to move forward with investigating livestock integration into these systems. We also work a lot with cover crops, lots of work with cover crops. So cover cropping is usually when we keep is when we plant some type of material prior or following the cash crop harvest, and we want to keep that soil covered. There's lots of interesting studies and interesting debate on the best way or what crops perform best as cover crops, and there's a lot of information out there. You could probably do days of webinars on that. In fact, I think there was a 3-day workshop a couple of weeks ago just on cover cropping. The point is, you're putting plant material you're covering the soil, growing plant material through that, and then you leave that on top of the soil, or they mow it in. Sometimes they'll let the winter kill it depending on the environment, or they're coming and till that prior to planting the cash crop. But we do a lot of work with cover crops. In certain areas, you'll have a summer cover crop, and in others, you can have a winter cover crop depending on the climate. We've done lots and lots of work with cover cropping. So I want to show a little bit of data. There's not two ways, there's probably several different ways to think about cover cropping. But one way to think about it is that we're adding organic matter to the system. So we grow the plant, we till it back in, we let it die, we're adding organic matter to the soil. We're keeping the soil covered, soil erosion, right? We're doing an excellent job of keeping the soil in place. We want to avoid that erosion. And if you'll remember to that first slide, a couple slides ago, I alluded to erosion and a loss of soil organic matter. So now we're kind of combating those two. In addition, depending on the type of cover crop you utilize, so a grass, for example, versus a legume, you can actually add nitrogen to your system. Generally speaking, grasses will hold and pull up nitrogen. So if you feel like you're losing nitrogen through the winter, particularly in our cases where we've got a lot of rain through the winter season, it's a great utilization of a cover crop. You can also use a legume to provide nitrogen for your system. So we do a lot of evaluating of those different approaches. For example, this comes from a study on the east side of the state, Linwood Farms and Anderson Organics. Those are two big onion producers. What we did here was plant two different cover crops, so sorghum Sudan and mustard. And actually, I've got a couple questions, and sorry, I didn't see those. Where does water management and hydrology fit into your overarching? I will answer that at the end. And Craig, what was the size of the plots? They were like 20 feet. Let me think about this. 20 feet by like 150 feet. And that is way too small. And the reason part of this is that we were trying to get replication. So we used it too small an area to do that. And we learned that the hard way, that they don't like that small area. And I will get to the other question later. But let me get back to this. So we're looking at two different planting dates and two different cover crops. So one is sorghum Sudan, as I mentioned, and mustard. Then what we did was vary the proportions of those rates to look at if there were any benefits to having, like, for example, I'm pretty sure you can see my mouse here. So 33 sorghum Sudan and 66 mustard. So that's just a percentage. 33% sorghum Sudan in this mix, 66% mustard. And we varied that. So 66% sorghum Sudan, 33% mustard all by itself, sorghum Sudan all by itself, and then no cover crop. Again, same thing at a different planting date to try to gain some information from whether these cover crops perform better at early or late planting dates. This right here, what you're seeing on the y-axis is dry weight in pounds per acre of weed biomass. So we also looked at weeds. So that's another benefit of using a cover crop, is to minimize weeds. So if you look to the, let me see if oops. Try this again. There we go. If we look on the right-hand side of this slide, you'll see those large bars. Those are the areas where there are no cover crops. And no cover crops at all. So you can see the large bars on the right-hand side in either the early or the late cover cropping. And these are dry weight in pounds per acre of weed biomass. So right-hand column where those yellow things are, that's how much weeds you have in biomass when you don't utilize a cover crop. So I'll just advance the slide, and this zooms in on that same slide, but removes that no cover crop to show you differences between the sorghum Sudan and the mustard. There's clearly some differences between the sites, the green bars being the Anderson farm and the orangish, yellowish bars being the Lenwood farm. But let me back up one. You can see a clear difference in the weed biomass per acre in crops that are, or plots that are cover cropped and those that are not. And I won't go too much more into what my opinions on mustard and sorghum Sudan, just to show you the types of things that we work on. We also do a lot of work with no and reduced tillage. So on the left side of your screen, that's a picture of a strip till in utilizing that strip tiller in a corn system. On the right-hand side, that's actually no tillage in a pasture renovation. We do no tillage work in vegetable cropping as well. So on your left-hand side, that's kale that was transplanted into an actual tilled plot. On the right-hand side there, both in those purple outlines, you also see kale that was tilled, and down the center there, where hopefully you can see my mouse, is no till. So you can see the difference between what happens when you go into a tilled system and a no-till system, but these are all transplanted. Just as an example, we'll then look at biomass. Clearly there's going to be a difference in weeds there. We'll also look at some of the soil functions that are occurring underneath those plants, because the two on your left and right in the purple were tilled, and the strip here in the middle was not tilled, and this is replicated and so on and so forth. But that's the kind of things that we're attempting to dive into. So we also do a lot of work with soil amendments. In particular, we've been on kind of a biochar kick over the last 2 years, I would say. We do a lot of work with compost, different types of amendments. One, how do you get that soil, or how do you get that organic matter into the soil, and how do they act as supplements to fertility? So can we use these amendments to maybe eliminate some of the fertilizer applications? There's also been a lot of interest in using the biochar not only as a soil amendment, but as a feedstock in the composting process. So we've done a lot of generation of compost that utilizes biochar in the feedstock, and how does that act on the soil, and then what does it do to the yield? So there's a lot of soil amendment work there. In general, one of the things when we start to think about adding amendments to the soil itself, we were trying to increase the organic matter. We're also trying to increase the space in that soil. So one of the measures that we often looked at, that's just a pretty simple concept, is bulk density. And I will explain bulk density very quickly. It's just in this case, it's grams per centimeter cube. So it's the weight per unit area per volume. So one way to think about this, and how I think about it, how I wrap my head around it simply, is that if you have a square box and I take a tractor and I run that tractor back and forth, and we compact that soil, then we've got more minerals per that unit area. So that's a compacted soil, and that means that there's more weight per area, and so the bulk density goes up. When we add applications of amendments, we actually reduce the bulk density. And by reducing the bulk density, adding that organic matter, we open up some spaces in between those minerals, and we allow water and air to exchange, and we improve habitats for soil microorganisms. So that's just one, it's kind of a simple thing that we measure, and a simple concept that we're trying to improve the soil by increasing the organic matter. So here's an example of that right in front of you. This is in potato, following different amendments. On the left-hand side, so we're talking about the y-axis, it's bulk density, and as I said, grams per cubic centimeters. X-axis, no amendment, so nothing was added to the soil. Biochar, compost plus biochar, a product that was co-composted with the biochar, and then a regular compost. And the point of this is that the numbers here, 0, 21, 24, 29, 29, all in yards per acre, is the amount of material that we apply to the soil. As the amount goes up, the bulk density goes down. So that I just wanted to provide you with a concrete example of that. One of the things why we look at adding soil or amendments to the soil. It's a concrete example of us adding an increasing quantity of that material, and the bulk density is declining. So now I want to get to the soil health, and I have seen that there are lots of questions, which is great. So I'll probably just try to power through and address all those, I think, because I really want to make sure I get through these concepts. So when we're thinking about these strategies, how do we evaluate whether they're working or not? One of the simplest ways is to look at yield, right? But sometimes functions underneath don't necessarily translate to greater yield. So we do a lot of soil testing and a lot of soil analysis. Soils are dynamic though, right? They are the result of a number of different interactions. There are different minerals, biological organisms, air and water exchange, heat exchange. All of these can vary according to the landscape in which the soil is situated. So it's a dynamic and interesting topic. Bias again. I'm starting to get excited about what I do. When we analyze the soil samples, we are getting into a window into some of that activity. You can't see all of it. It's not like live streaming this activity, but we're getting a snapshot in time on what we've done to the soil and how the soil is responding to those strategies, or like amendments or cover cropping or tillage, for example. I imagine that many of you have seen something like this. If you have any familiarity with taking a soil sample, you get a soil report. You get something similar to this. It may not be exactly the same, but generally speaking, on your left-hand side over here, we've got the different tests, the analytes, the method that they utilize to get at those numbers, and then the actual values themselves. Then you'll often see some type of soil test rating, very low, low, medium, optimum, very high. And this varies from lab to lab on how they present these types of data, in particular the graphing. The methods can vary. There are different ways to get at different functions in the soil, and different labs will have different approaches. One important thing to know, if you utilize a soil laboratory, remain with the same laboratory over a number of years, because as I said, those methods can change from lab to lab. And if you were to compare, say every 2 years, or maybe it's every 3 years, and you switch labs in between there, the methods may change and those values may change. You can actually look these methods up if you're interested, and you could switch labs if you were sure that they were using the same method to evaluate what you're interested in looking like with phosphorus, for example. So just as a note, a piece of common sense or whatever it is, helper maybe, stay with one lab when you start to look at soils. So to my earlier comment about those graphs where they have low, medium, high, what those are presenting is a correlation. So on the y-axis here, you've got crop yield going up. Bottom, you've got the soil test value. In the low situations of those nutrients, if you add more, you're going to likely see a yield increase. In the medium sections here in this middle column, maybe you will see, sometimes you'll see yield increases. And then in these high sections where it tells you on the soil test report for whatever nutrient you may be looking at, the high means that you're not going to see it's unlikely that you'll see a yield increase. So that's where that basis is from. But all of these soil analytes come from using chemical extractants. I use a bunch of different chemicals, and I'm going to show this on the next slide, and we extract out what those compounds are. We measure nutrients that are expected to be plant available. If we measured all the nutrients in there, it doesn't give us a useful piece of information, because there are nutrients in the soil that remain there and that are kind of tied up, for lack of a better way to describe it. So we measure the nutrients that are expected to be plant available. And these measurements are then correlated with yield increases. And we have lots of information, years and years of data on what those numbers are and where they are for certain crops and certain soils. So it's very reliable. But as we move towards the kind of newer soil health measures, we're going to incorporate different things into our soil testing. So now we're using, again, chemical extractants to evaluate those nutrients in the soil. And as an example, you'll see here on your left-hand side, the plant nutrient that we're looking at, and on the right-hand side, some of the common extractants that we use to get at that information. So for example, nitrate, that first line there, potassium chloride, or calcium chloride. You'll notice here on the third line down, left hand, that's phosphorus. There's a number of different ways, three different ways to get at that phosphorus. And some of that has to do, sorry, spiders dropped down. Some of that has to do with the soil itself. And we've, after years of research, have figured out the best methods to get some of that information out. So that's just telling us about the chemical nutrients of the soil. That's just a little bit of a review to have a basis for what we move into next. But think about this. Does anyone think that the soil is just those chemical properties? No, if you're looking at this picture, is the first thing that you think of is that the soil is just a chemical entity? No, there's physical properties, right? There are biological properties in addition to that. Soil microorganisms, there's sand, silt, and clay. There's different textures in the soil. There's plant roots in the soil. There's all kinds of things going on there that a chemical approach doesn't necessarily tell us about. So we have physical properties, chemical properties, and biological properties of the soil. Physical properties, as listed on the slide, are like texture, sand, silt, and clay. It's a proportion of sand, silt, and clay. Horizons in that soil as we move down, different structures in that soil. We have chemical properties, which we just kind of talked about, pH, inorganic ions, phosphorus, those types of things. And then we have biological properties. There are organisms in there that have different sizes of their populations, different diversities within those populations. We have a food web. One guy is eating one guy and the other person is eating the other thing. And then as they excrete that out, that becomes a nutrient for something else. Then we have organic matter. There's decaying roots, decaying leaves, and those biological organisms die and decay. So physical, chemical, and biological properties, those are all part of the soil. As our understanding of the soil has advanced, and this is not like really a new concept, but you're going to start seeing some of this available at some of the soil testing labs, we've come to maybe not even agree upon, but there's a concept of soil health. Again, soil quality, I'm going to interchange the two, but soil health is defined as the continued capacity of the soil to function as a vital living ecosystem that sustains plants, animals, and humans. So we've been looking at chemical extractions for a long time and thinking about how those relate to yield. And we've been discussing that we're missing some of these other properties, other physical and biological properties of the soil. So this concept is trying to identify and account for the vitality of the soil and what you're doing to it, what practices you have, what effects did that have on those biological organisms. What we're also trying to avoid is degraded soil. We don't want to have a degraded soil. We have like a healthy soil and it's some wide spectrum of where that, kind of a dial is, but we definitely don't want to be on the side where it's degraded. We don't want to have like a surface sealing, as you see up in that upper left hand, or a soil that has low organic matter, or one that's compacted. The soil quality and soil health might, like as I said, be a wide range of values in there, but what we're ultimately avoiding is degraded soil. We're avoiding degraded soil because when we get degraded soil, we get larger environmental degradation. So for example, erosion. On those pieces of soil, let's say portions of soil that will erode away, there's phosphorus. As that phosphorus will get into a waterway, you can see eutrophication, where the organisms in that water utilize that nutrient and grow quickly, thereby causing a reduction in oxygen. And imagine some of you have seen ponds like this, or areas where there's just so much nutrients that you can actually shrink the pond itself. So by maintaining the soil, we're trying to help the environment at large. And remember that original slide where I said that the soil, interacts with gas and water filtration. It's kind of like the skin of the earth. I've had a colleague say, we're talking about maintaining the skin of the earth. Good soil, reduce environmental degradation. So, as I mentioned, soil health, there's a number of different kind of frameworks for this. One of the more popular and probably well developed as far as a system of evaluating this is the Comprehensive Assessment of Soil Health, and that's called the CASH. That's at Cornell. You can send your soil samples to their laboratory, and you can get a soil health measure, a measure of soil health. And I will show you what you get. Now, remember, I said that there are physical, biological, and chemical properties that we're trying to get at, not just the chemical. This is an example of a report, what you get from the CASH system. So I'm going to go through it really quickly. The top is measured soil textural class, so that tells you what the texture is, a silt loam, and then it tells you those percentages. You can get that type of texture at many labs already. So in the top portion, purple box, that's all the physical indicators: available water capacity, surface hardness, subsurface hardness, aggregate stability. Those are physical properties that we can measure, or rather they're physical analytes that we can measure. Then you get a value and then a rating. This rating is taking all the samples that they receive and basically creating a mean out of that and positioning your value within those groups of samples. There's a little bit of some interpretation here because a lot of those samples are on the East Coast and our soils are a little bit different. But as an example, so if you continue down this slide, you see in the black and the green there, biological, organic matter, ACE, soil protein index, soil respiration. Now we're getting at that biological function. As we advance down to the chemical brown portion, we're talking about those values that we discussed earlier. Some of these chemical properties that we've kind of known, we've known about a lot of this anyway, but you're used to seeing these on solar reports. And then they provide an overall score, but I won't go into too much detail. There's some math behind that, but just as an example that these soil health, there are laboratories out there that provide all of these into one neat package. And I also believe Oregon State might be doing this as well. So to be clear, some of these methods have been used in research for a number of years, and they're just now becoming available at commercial labs, and this is an evolving process. But I wanted to point out some of these things that you'll likely see, or you may have already seen or as an option in from some of your labs. You'll most likely start to see some physical, if you already don't have that option, wet aggregate stability or water holding capacity. To the answer of someone earlier, or the question of someone earlier, we can address the hydrology of the soil by getting at functions like this, wet aggregate stability and water holding capacity. Those are a little bit more involved to measure, but they're starting to be offered in commercial labs. And again, biological stuff that you may see on those reports, soil respiration. They call some things active carbon or labile carbon. Carbon is available to those microorganisms to utilize as energy and to utilize as food, and biologically available nitrogen. So nitrogen that's readily available for those microorganisms. So you can see that we're looking at the biology of the soil, but we're also looking in the environmental, how much water does this soil hold, which also affects the biological organisms. But before I go too deep, I'm not sure how much background you all have in soils. I want to discuss aggregates really quickly because this gets into carbon and biological function and water holding capacity. So here is a visual depiction of a soil aggregate, and this is from a scanning electron microscope. This image shows both minerals and organic matter bound together. When minerals and decomposing soil organic matter bind together, the spaces and gaps are created in that soil. And in those spaces that are different sizes, we often talk about like macropores and micropores, air and water can move, and organisms can live and cycle nutrients, and carbon can be stored. So we spend a lot of time talking about soil aggregation. How does a soil aggregate as a verb? And here is a illustration of my own doing, which is not that great because I'm a terrible artist. But so starting at the upper left-hand side of the slide, we've got mineral particles. So that's the sand, silt, and clay. We've got microbial byproducts, which can be their bodies. A fancy term is microbial necromass, or nutrients that are sloughed off. We've got decomposing organic matter. Think breaking down leaves, twigs, grass, corn stover. We've got fungal hyphae as an additional microbial property, or rather characteristics. And when you combine all these together, we get soil aggregation. So the microbial byproducts, the fungal hyphae, and the decomposing organic matter kind of act as glues between those mineral particles. As I said, you get different sizes of aggregation. And then between those aggregates, we have spaces where air and water can move. Interestingly, about 80% of the soil organic matter in general comes from the microbial byproducts here and fungal hyphae. So that's kind of interesting. It shows how important those biological organisms are. So when we used to think about soil organic matter, we used to use the term humus. It's an interesting way to think about soil, and it's an interesting way to think about carbon. Now, if I'll go back one slide here, this decomposing organic matter is critical to this aggregation. It also acts like a glue, but what this decomposing organic matter does is it provides spaces for water to adhere to, and it provides edges, a simple way to think about those nutrients sticking to that. And as I said before, if you remember several slides ago, when I was talking about adding organic matter and decreasing that bulk density, big important component of the soil. Some of that, and you can probably split hairs here, but some of that decomposing organic matter is that microbial byproduct. So that kind of organic matter that's in that system is really important. So what we used to think about the organic matter was that it was called humus. And we talked about different proportions of the soil. So this diagram is just so when we think about soil, volume of soil, half of it roughly, if you see the silt, clay, and sand up there, roughly half of it is mineral, about a quarter of it is water, a little less than a quarter of it is air, and then some small percentage of that is organic matter, the remainder of that volume. And within that organic matter, then we talk about different properties of that organic matter, and also we're talking about carbon. So that's where a lot of this motivation comes from, storing carbon and thinking about carbon in the soil. A portion of that is active organic matter and living organisms. And we used to think that, let me advance this slide. We used to think that the humus, or the organic matter that was in that soil, we kind of called it recalcitrant, was this amorphous, like wieldy compound that was just resistant to decomposition. And that was a way to store carbon in there, to keep some of the carbon in the soil. And these were evaluated by using chemical extractants with a very, very high pH, alkali solution. Years and years and years and years of debate over whether this is the correct approach to identify this organic matter and think about managing organic matter, because that's what we're really ultimately thinking about doing, is getting that organic matter into the system. How can we keep some of that there, but also provide fuel for those microorganisms? Turns out, and depends on who you ask, but it's not wrong. But really what keeps organic matter in the soil is its location. Remember 2 slides ago I said aggregation is critical to the soil? Well, the current view is that location of that organic matter, whatever it is where it's located is the critical thing in deciding how that organic matter is either available to those organisms or stored in the soil. So now we're starting to think about the location of that organic matter in the aggregate. So once the organic matter enters the soil, its persistence depends on the location. And that has a lot to do with tillage and a couple of other property or strategies that now we're kind of thinking a little bit different about. So again, here's another terrible illustration drawn by me, not an artist, clearly. We're talking about the soil aggregate. Inside that soil aggregate, there can be soil microbes. There can be compounds of organic, there can be carbon, there can be different stages of decomposition for that organic matter in that aggregate, outside that aggregate. You can have micro aggregates where actually organisms don't get to, and that's where portions of that organic matter are stored long term. So we're really thinking about those microbes. And the newer tests that look at these in soil health focus on thinking about not only the microbes themselves, but the food for the microbes. So we're not just thinking about nitrogen or phosphorus, we're thinking about that carbon that those microbes utilize for their own growth, maintenance of their cellular needs. We can identify them, and we can identify them by a respiration. So on this slide, we're looking at, on the top side, or excuse me, where my pointer is, the test name. These are analytical approaches that you may see that are kind of evolving in soil health. Mineralizable C, which is basically microbial respiration. We're seeing how much, or what are the, how quickly or how readily can these microbes access this carbon, and we measure their actual respiration. We measure the CO2 coming off the soil as a, as a proxy for their activity. So that's like instantly available. Are the practices we're doing providing these organisms with food right now? We can measure that. It's just a simple measurement of CO2. These other two get at potential food sources. Interestingly enough, they're also linked with carbon storage. So there's a little bit of breakdown on these two. So POC, it's permanganate oxidizable carbon. It's a microbial food source, a way to think about it. And palm C, which is particulate organic matter carbon. And that's also like a potential food source. We're looking at, are we creating the environment for those microbes to live? So the first one is respiration. We're looking at how well they're doing, how they're doing in there. And then, are we creating an environment where they have food? So it's kind of like looking in the pantry. If you think about carbon in the soil, we often look at total carbon, so total C, or organic matter. That takes a lot of time to change, like decades, 5 years, and it's difficult to evaluate whether your practice is improving that because it's so slow to change. These types of processes and evaluations, in particular the POC and the palm C here, give us a little bit better insight on a shorter time scale to see that whether we're kind of putting food in the pantry, so to speak, over a year, maybe 2 years instead of 5, where we couldn't really see what was going on with that carbon. And in addition to that, I had mentioned biological nitrogen, ACE protein, and water extractable organic N are other ways to get at the nitrogen component of the microorganisms. Are we creating, again, food, a different type of food source than the nitrogen? They need both of those to do well. So we're looking at that pantry, kind of taking a look. Hopefully we're stocking some, whatever it is, cans of beans or something. So in general, what we're trying to do with this is increase the soil quality or the soil health of the soil. So in that top section here, you've got soil A in the blue. Degrading is going down, aggrading or increasing is going up, and then there's kind of like an equilibrium in the middle. Bottom in the brown, look at the aggrading, the degrading, and then equilibrium here in the middle. But you'll notice between the two, the slope on this one here where my cursor is going up drastically different than soil A. The point of this is to say that soils are going to respond differently. So it may take longer in some cases for the soil to not adjust, it's not really a thing, but for our values to influence certain functions within the soil. Some soils will respond very quickly. So the soil itself has the type of soil has an influence over how great of an increase that quality or that health can be. And in some cases, you're going to get to a maximum. I don't want to say that it can continue always increasing your soil health, your soil quality. The soil can probably only hold a certain amount of organic matter, and that has to do with the texture and the clays and that. But you can increase the soil quality or the soil health and reach a new equilibrium. So that's what we're trying to do. And to do that, and just to kind of look at management strategies at the end here, and then I'll take a bunch of questions because I think I'm right at time too. We think about the soil health continuum. Lower on the left-hand side of the slide, and annual cropping systems, excessive tillage. Monoculture, there's some argument there, but we know that tillage breaks that up, excessively tilling it. You kind of move towards higher soil health, no-till and rotation, tillage and rotation, no-till plus cover crop plus rotation. And get into in theory, like this is a theoretical approach here, highest soil health, pasture, forage hay, biofuels, the feedstock, CRPs, restored prairies, very little tillage, putting a lot of amendments out there on that soil, and we've got the high soil quality. But again, this is into relation to how we use that soil, as far as we can't just dump 20 pounds of compost on something we're trying to grow, right? We need some soil in there, but it gives you a theoretical framework for this. So I know I've thrown a lot of information at you all, and I noticed there are lots of questions, so that's good. So at least you can yell at me or be irritated or entertained. But thank you for listening. There's my email address. If I don't get to a question you have, or I don't explain it, or I don't have the answer, I can direct you to someone who does, and or find that information for you. So I will stop sharing, and I think I'll maybe let Hannah take over, or I can actually do the questions too.
Yeah, we've got quite a few questions there in the Q&A. I think the first one is, where does water management and hydrology fit into your overarching categories and your research areas?
So that's a great question. Water is really hard to deal with and to measure in the soil. So we haven't done any studies that directly evaluate low approaches to irrigation. We generally, when we're working with farmers, allow them to irrigate at their whatever they feel comfortable with. We have recently started looking at water holding capacity and volumetric water content. So it's kind of the same thing. So there's water that is there in the volume of soil, and then there's available water, which has to do with the potential energy of the soil. We have not done any, to answer your question, we have not done any specific research with those historically. We are now starting to incorporate that water holding capacity into future stuff to evaluate where that, you get this curve, and we're trying to evaluate how that curve then translates to something that's usable, because we can generate all these curves, but if it's nothing that like a farmer can go out there and squeeze it in his hand, it's not really that much value. So we haven't done that historically. We're starting to incorporate that now. But I can tell you that as far as the amendment approach, organic amendment does generally increase the volumetric water content in that aggregation. So we kind of go at that indirectly by adding the organic matter and trying to increase the aggregates in that soil. Hopefully that answers your question. And like I said, shoot me an email if it doesn't, and I can go on further. I could go for hours. It's probably bad.
Yeah, and we are bumping right up on that 1 o'clock hour. So I know that you said you had a little extra time. Should we stay on till, I think we'll keep it on until about 1:10, and then we'll cut it off. And all the questions will get emailed, and then we'll send answers out with the recording next week.
Great.
So an interesting question. Is there anything that can be done to build back the degraded soil in a forest after an extremely hot forest fire?
Oh, that is a good question. And I'll precursor this with, I do not work in forest systems. I'm going to speculate. So coming from the biochar, the interesting thing about biochar is that forest fires and or fires in the prairie or grasslands occurs at some known rate in history. You can go out there and actually evaluate, look at these black carbon, basically. In some ways, and it depends on the system, that fire can be healthy. That biochar is going to have so the burnt carbon, basically the burnt black carbon, is going to have a profound effect on that soil itself and actually retaining nutrients. In general, often we just add organic matter, but there's going to be some interaction with that biochar, and I'm not saying that it's going to fix itself, but that black carbon, or what I'm referring to as biochar, can have repercussions long term that may actually help the soil improve in those forest systems. But I could look that up and look and see if anyone's done research on that. But I would imagine that just even adding organic matter is going to be beneficial if you're trying to manage that.
All right. Is there a simple way to do soil analysis without having to send it to a lab, like some home test? Does that exist?
Yeah, absolutely. There are a couple. So there is a, if you email me, I will send you links to this, but WSU Puyallup soil, that's a website. I think you just search soil in WSU Puyallup. On that website, there are a couple of different things. So you can analyze texture. There's actually a hand approach to analyzing the texture to give you a pretty good estimate. There are ways to do bulk density by just using a coffee can or a small can. You can evaluate the bulk density of your soil. You can actually also evaluate the moisture content of your soil by just using your oven. There are nitrate strip tests that they actually use in pools that it's a little bit more involved to do at home, but it can give you a pretty rough estimate of the nitrate that is in your soil. And the nitrate is the one that's mobile. So it moves through the soil quickly and can contaminate, but it's also the one that generally speaking, most plants uptake nitrate. So there are a couple different ways to do that. Some of the other stuff, you have to send it to a lab, but there are some simple things: bulk density, texture, and I said nitrate. You could just do at home.
Awesome. We've got another question. We've got quite a few actually, but how does one start to approach evaluating soil health in permanent crops like orchards or vineyards?
So I think so. That's a great question. I think I would contact the lab that you're going to work with, or an agricultural professional who's dealing with these soil health. So bulk density is not going to change that much, right? Because you're growing. We're not changing the bulk density. We're not tilling, but those measures of carbon, the palm C and the epoxy, probably even more so the palm C, would give you some interesting information about how those nutrients are cycling, or what you're doing is influencing those soil processes. So the vineyard and the orchard is going to, again, I don't do research in those, but that plant root is going to supply some amount of carbon to the soil at some rate. So if we can get in and get information on that epoxy and that palm C, maybe we know that we're doing a good job in providing nutrients to those microorganisms. And you probably would also focus more on the microorganisms there. And there's different ways to do that, to see if what you're doing above ground is affecting their vitality. So you probably will get less from the physical stuff and more from even just traditional chemical stuff, and more on that biological. If that makes sense, hopefully that.
Thank you. Does the research on biochar and compost amendments suggest that compost is most effective at reducing bulk density?
It is the quantity of material is actually the simplest way to look at it. It in that case, because we applied, so in that research, we applied carbon at a certain rate. So the compost actually went out at the highest rate, and because there was more carbon in the biochars, it went out at a lower rate. So it's really just the quantity of material. The composting biochar has to do with different nutrient availability.
Another question about pesticides, actually. Do you have any plans to introduce pesticides to any of your plots to evaluate their effect on soil health?
We don't. Generally speaking, we deal in organic systems, and that's a whole nother level of science that I don't get into. But there are people that do that, though. There are people definitely evaluating that. And in addition to that, there is a woman in Mount Vernon. If you look up, WSU has like a soil health initiative, I believe is the term. Deirdre Griffin, she is the new professor of soil health, and so they're kind of generating a lot of this data right now and building the soil health program in the state. It's really exciting, and she's great. Contact her, ask her. And I think they have a website too as well, and she would have probably more specific details about maybe the pesticide use.
Awesome. We still got a couple more. On a no-till wheat farm, does the soil bulk density increase over the years?
A no-till wheat farm. A no-till wheat farm. You're probably going to get, I would imagine that it decreases, because you're just, even though you're extracting the top portion of the biomass, you're still going to get some of that carbon coming in from the roots. And if you're not tilling, you're not breaking up those aggregates. And if you're feeding that microbial population, it's either going to decrease a little bit or probably just stay the same. I would be surprised if it increased. Unless it was like well, no, because it's no-till, so you're not compacting it. So I would say probably stay the same and decrease.
Here's one about conventional agriculture. How convinced are you of the value of biochar in conventional agriculture?
That's a great question, and that's a 20-minute answer. It depends. Biochar alone, and I'll try to be succinct. Application of biochar alone, not composted with anything, will affect your yield. Oftentimes it decreases the yield. This depends on the type of soil. This depends on the texture of the soil. How long that persists, I cannot give you a number. If you add it alone, what you're going to likely get is mineralization or immobilization, of the nitrogen, because it's a hell of a lot of carbon. So you'll see probably a decrease in yield, but over time that will probably change. It's going to affect your aggregates for sure, right? Because you're adding a material to the soil. It's probably more value if it's composted, because it brings more nutrients to the system. You can use it if you want, but I think your expectations should be realistic in that you probably will see a decline in yield at first. There is some value there, certainly if you're thinking about carbon and storing carbon, but I don't know the overall cost. Is that cost effective? Can you apply biochar at a high rate? Are you willing to spend that kind of money? That I don't know.
Alrighty. Thank you so much for all of you for joining us here today. And thank you, Nathan, for speaking with us. We just had a couple of questions that weren't able to be answered. So I'm going to go ahead and send them to you in an email, and we will send them out with the recording to everybody who is here today. We hope that you enjoyed and learned something new today. If you have any more additional questions, please email me. And we hope to see you in December for a legislative update. Thank you all.